Hello everybody, so this is going to be a whistle-stop tour through Learning Outcomes 7, which is generation, transmission and distribution of electricity. Okay, so first of all we're going to talk about the generation of electricity, and there are two types of sources. There are renewable sources. Now the renewable ones are in nature. So we've got hydro, which I'll explain a bit more in detail in a minute on the next slide, but that's using water. Solar, you know all about solar panels already. That's obviously using sun, and you have photovoltaic cells, and solar panels only produce DC, not AC. Then we've got wind source of power, and that is AC. That drives a turbine, which drives the generator, your AC generator. Then we've got wave power and tidal, which are very similar. And again, it drives a turbine that generates AC. And then we've got our non-renewable sources. So these are all the dirty ones: the fossil fuels, oil, coal and gas, which we're trying to move away from. Funny enough, in this country, we use gas predominantly. We are a big gas consumer, and there's also nuclear. Now, France is a huge use of nuclear power, and we are currently actually in this country building another one at the moment. So we're sort of trying to move in that direction, because whilst it's not renewable, it is cleaner, much cleaner than the fossil fuels. And then we have another energy source in the form of batteries, which we're all very familiar with and very useful. So I would recommend that you are able to list renewable sources and non-renewable sources, and that you know a bit about a battery. I'm going to explain them on the next slide, but for the exam I would just make sure you can list these and understand how they work, and the same for the non-renewable sources. So going on to renewable. So these are the ones that I was talking about occur in nature. So hydroelectric power, that is water that is stored at a height, so in a reservoir, and it flows down through a turbine, which then drives an AC generator. So here's your reservoir of water up here, and this moves through this channel, driving this turbine, and you can see the generator here, and that generates your power. And then we have a wind turbine, which is similar. It's just the motion of the wind turns the blade, which then drives an AC generator, and the output from the generator is then connected to the public supply, the same as in the hydro example we've got there. So it's a really good idea to be able to list your renewable sources, but also to be able just to describe a couple of them, because it may well say list 4 renewable resources and describe how one works. So make sure you can understand at least 2 of them, but that you can list a good 4 or 5 of them. Oh, and then we've got a picture of a wind turbine, in case you weren't familiar with those. Right, so now we're on to the non-renewable sources. So these are the dirty ones, the fossil fuels. These are what we associate with power stations, and we need to know how this is generated, how they're used to generate electricity. So in a power station, you start off with your energy source, so either oil, coal or gas at this point. They're burnt, they're set on fire, and then the heat is used with a big supply of water. So that's one of the disadvantages of these power stations, is that they use a huge amount of water, and it's used to produce steam. Now this steam is forced under pressure down a tight tube, and it's that pressurized steam which then turns those turbines again, and the rotation of those turbines turns the coils in the generator. So this final two stages, the turbine and the generator, is the same as the renewable source of energy. So the only difference you need to remember between the two is how you get that turbine to rotate. In a power station, it's your fossil fuel that's burnt, and the heat is used to heat up water to produce steam, which is forced under pressure to rotate the turbine. Okay, and then I've got a picture here of how that works. Okay, I've also included this PowerPoint on the email as an attachment, so not just the video lesson, so that you can go back and have a look at these slides at your own pace. I'm just going to do a quick chat through now. Okay, so we talked about renewable and non-renewable energy sources. So now the final one we need to talk about is your batteries. And obviously the huge benefit of a battery is its portability. Car batteries, torch batteries, that's the main benefit of a battery. It stores energy and you can take it anywhere. Unfortunately, there are quite a few limitations with batteries. They have a small capacity. Obviously, they need to be replaced when they run out. But if you do have rechargeable ones, you'll all know you have to recharge them really regularly. And that's frustrating. Mobile phones being the most annoying one, I would suggest. And to get more power, obviously you need a much larger bank of batteries, and that takes up a huge amount of space. So they're not very efficient space-wise. So that's your batteries, the benefits and the limitations. Just check as well, look up what is in a battery. So you've got that chemical reaction that occurs inside the battery that generates the electricity. That's in the handouts I sent to you previously. So just make sure you know in your head what's going on inside the battery and the benefits and the limitations of batteries. Okay, so this looks like a confusing picture. It's not too bad. It's just telling you the generation here and the voltages that are at each stage, which again is something you should probably try and remember. It does come up quite frequently in the exam. So all power is generated at 25 kilovolts. Then you have your step-up transformer, and the electricity is then transmitted at generally 400 kilovolts. Okay, then it's stepped down to safer voltages, which are then distributed to the domestic and industrial properties. So moving on, these are our voltages, which you need to remember. So generated at 25 kilovolts. These are the three transmission voltages in the high power cables overhead. 400 kilovolts, 275 kilovolts, and 132 kilovolts. And then your distribution voltages, obviously this one, the 400, 230, we're really familiar with. Just remember, 400 is your industrial application, that's your three-phase, and your 230 is your domestic. And big power users, factories, will use your 11 kilovolts. So you've had your electricity flowing through your transmission lines, and then it needs to get stepped down to the safe voltages, and this is done at the substation. As it says here, it provides an interconnecting and isolation points in the network. So in a substation, we have the step-down transformers. Here's a picture of a classic transformer for you with the windings. So if it was a step-down transformer, it would have more windings on the left where the supply is coming in and less windings on the right, as you can see here, for the distribution voltages here, for the lower voltages. So big number of windings to small number of windings on a step-down transformer in your substation. And we also have isolators there. And we also have big switch gear and fuse gear. Sorry, that says behind there fuse gear. So we talked a bit about transformers at the substation, and this is what they look like. So on the generation side, you would have the step up transformer. So that's this one here. And as it says here, it's from power stations and it transmits in high voltage. So you've got the smaller number of windings on the left and the larger number of windings on the right, indicating that you're stepping up that voltage. Okay. And then you've got your step down transformer, which occurs in your substations to distribute electricity into domestic and industrial premises. And again, you've got your less turns on the secondary side, which is where you're stepping down your voltage for safe distribution. Okay, so we're still talking about transformers now and the basic operating principles. Because they're working so hard, their core is being magnetized and demagnetized. There's heat that is being generated there. And we've got 3 different types of cooling methods for transformers. So we've got the basic air-cooled ones, and air is simply passed over them. They're stuck on the edge of outside, so the air passes over them. But for a more efficient cooling method, you would use oil, and they have the windings. They're immersed in the oil. So the actual transformer itself sits in a box, which is then got oil poured into it, and it's got cooling tubes on the outside, so that oil is continually circling, cooling down and cooling that transformer. And in a similar way, gas can also be used as a cooling system. Okay, still on transformers. So with that heat that's being generated, that's a type of loss. And these are losses that you find in the core of the transformer. And one is hysteresis, which is a bit of a strange name. And this is referring to the loss of energy. It's due to that core that's being magnetized and demagnetized continuously. And where that magnetism has to change direction, there's obviously a slight loss of energy in the changeover cycle where it's sort of pushing against each other, and that's your hysteresis loss. And we also have eddy currents in the core, and that's in the iron core, and it's where the alternating magnetic field, it induces an EMF within that core itself, not just in the windings around the core, and these currents are circulating and they produce heat, and that's your heat loss. That's your eddy currents perform the heat loss for you. And also in your windings you get losses, and that's due to the resistance of the actual windings, and that's where losses occur there, the copper loss that's called. Now, these losses can be reduced by laminating the core, by having slices of iron rather than a solid block of iron in the core. And so that's an efficient way of reducing the losses. And finally, there's a formula, as ever, and this refers to the stepping up and stepping down ratio between the primary and the secondary transformer. So VP is your voltage on the primary, and that divided by the voltage on your secondary is equal to the number of turns on the primary divided by the number of turns on the secondary. And this is a ratio. You would call this a ratio. So what I've put here for you all is a question that I want you to have a go at home, and I would like you to bring it into college when we first meet the first week, and I'll see how you got on with it. So I know that was really quick run through of all those key points. These are the essential parts that I would like you to go back over, look in the handouts that you've already had about all of this work, and make sure you know everything that I've just run through here. Okay? Any questions, bring them to class, and I look forward to seeing you all next week.